All right, example 7. So here we have a different kind of function. Notice that we have two rules here. And you might be thinking, well, wait a minute, we can't have two rules. We said that there can only be one rule. But notice here, this tells us when to use each rule, and there's no overlap there. So it's okay. For example, when x is 10, 10 is greater than 1, so we're going to use this rule. It's just the rule changes for different values of the domain. And this is called a piecewise function. So as long as there's no overlap in your conditions, so if there's an overlap here, then you would, like if x is 1, if they both had equality, it would be confusing because f at 1 would be two different values. But because there's no overlap, we're okay. All right, so we want to find f at 0, f at 1, and f at 4. So f at 0, the input 0 is less than 1, so we use the first rule, 3 times 0 minus 5, which is negative 5. F at 1, we have to use the first rule because that's where x is equals to 1, or is equal to 1, excuse me. So 3 times 1 minus 5, which is negative 2. So notice for that input, we don't plug in both rules. It wouldn't make sense to have two outputs for one input. And then f at 4, now 4 is bigger than 1, so we're going to use the second rule. 2 times 4 squared minus 1. 16 times 2 is 32. Minus 1 is 31. All right, so we'll work more with piecewise functions and graph them in the next section. Example 8. So far we've been given the x and we solved for y. In this problem, we're actually given the y coordinate. We have a function here and says find all values of x for which f at x is 0 and f at x is negative 10. This is basically two different problems. So let's do the f at x equals 0. This means that y is 0. What's x when y is 0? Well, what we're going to do is say, okay, well, we know that f at x is our formula, x squared minus 7x. We want the answer to be 0. So solve for x. Well, this can be solved by factoring. X is common to both terms. Factor it out. And so x is either 0 or x is 7, right? That's just solving a quadratic equation using factoring. The next example, or the next problem, the f at x is negative 10. We'll handle this separately. Now we want our formula x squared minus 7x to have an output of negative 10. This is also a quadratic equation, right, because of the x squared. And so when we solve quadratic equations, we move everything to one side. So bring the 10 over, plus 10 equals 0. This one can also be solved by factoring. We have a trinomial that we can factor. If it didn't factor, we could use a quadratic formula. So just because things don't factor doesn't mean we can't solve, right? But the factors of negative 10 that add up to negative 7 are negative 5 and negative 2. And so this will give us x is 5 or x is 2. So we had two answers for both of these. That's okay. This is telling us that, if we wanted to think about which ordered pairs are associated with this function, when x is 0, y is 0. And when x is 7, y is 0, right? We were given y is 0. For this one, x is 5, y was negative 10. And here, when x was 2, y was still negative 10, right? So when you plug, if you wanted to check your work, you would just, plug in 5 here. 5 squared is 25. 7 times 5 is 35. 25 minus 35 is negative 10. That's the output we wanted to get. You could check all the others as well. Now these are the answers here. We want the x's, but I just want to point out that we do have these ordered pairs associated with the work that we did here. Okay, so now we're on to domain in turn when we have formulas. So here, this takes a little more work than when we have a list of ordered pairs, because we have to think about which numbers are okay to plug in, and apply this rule to. We can't always apply the rule to every possible number. So the domain is implied by the formula. It's not really explicitly stated, but you can figure it out by, looking at the formula. So this y is 3x plus 5. You just want to think about, what's your rule here? What am I doing? Can I do this to any number? This rule says to take the number times 3 and then add 5 to the result. Well, there isn't any number that you can't multiply times 3. You can always perform multiplication, and you can always perform addition. And so the domain here is all real numbers. You can write all real numbers if you want, but of course you should know how to use interval notation, and sometimes I'll ask specifically for that. So this would be your interval notation answer, negative infinity to infinity. All right, let's move on to B. So B, we have this rule that, here we just plug in the input on the top. On the bottom, we're going to square the input. That's not a problem. And then subtract 9 from that. That's not a problem. The operation that can become a problem is the division. We cannot divide by 0, right? And so what we need here is for the denominator, the result we get in the denominator, to never be 0. And that's going to be 0 when x squared minus 9 is 0. So let me write that down. When is x squared minus 9 equal to 0? We need to omit those values from the domain. Whoops, omit. Well, that's an easy thing to answer because x squared minus 9 factors. You can also say x squared is 9 and use the square root property to solve, but we'll factor. So x is negative 3 or 3. These are the numbers not in the domain. Everything else is fine. So the domain, let me give it to you in interval notation only since I'm running out of room. So you've got all real numbers here. That's your whole line. You want to just take out, you've got your whole line here, 0, here's negative 3, and here's 3. You're only going to delete these values. So you'll have negative infinity to negative 3, right? And then you have a gap. So you use union to unite it to the next interval in here, negative 3 to 3, and then union 3 to infinity. You could also write down, all real numbers except negative 3 and 3. And you can use inequality notation as well. But interval notation is usually what we'll go with. Okay, so don't forget about this gap. What a lot of students do is they only write this. They forget about this one. There is these values in between negative 3 and 3 that are in the domain, so you want to include those. Okay, let's do C. Here we have a square root. Now, you should have worked with imaginary numbers before, and so if you're going to allow imaginary numbers, it's okay to have a square root of a negative. But with functions, we usually deal with just the real values. So we want the output to be a real number. It almost looks like one word. Well, in order for this to be real, this can't be negative. So we need 3x minus 8 to be bigger than or equal to 0. If you solve that, you're going to get the domain. So 3x should be greater than or equal to 8. X will need to be greater than or equal to 8/3. When you plug in 8/3, notice the 3's would cancel, and 8 minus 8 is 0. So that's your cutoff between when this result is positive or negative. Make sure you get your inequality the right direction. Don't forget, if you're dividing by a negative, to switch the direction of the inequality, because that, of course, affects the domain. But we divided by a positive here. So the domain in interval notation would be 8/3 to infinity. Okay, one more here. In D, we have got G as a function of T. We have a 5 on top, that's fine. The t squared plus 1, we can do that. Again, it's the division, so this can't be 0 on the bottom here. Well, notice that in this case, t squared plus 1 equals 0 would result in an imaginary solution. Take the square root of both sides and you'll get plus or minus the square root of -1, which is plus or minus I. That's telling me that, and think about it, if you square a real number, not I, but some real number, the smallest thing you could get is 0, and that's if t is 0. And then if you add 1 to it, the smallest thing you're going to get is 1. And so t squared plus 1 is bigger than or equal to, whoops, not 0, but 1. It is bigger than or equal to 0 as well, but that would be true. But specifically 1 is the smallest it can be. And so this is never going to be 0. If t is real. And we're only going to work with real numbers here, so we have no problem. The domain here is all real numbers. Okay? Is never, this should say if. Sorry, I write too fast sometimes. I will make mistakes sometimes. If you catch one, let me know. Okay, the next example. Here we're going to write a function. It says an open-top box is to be constructed from a rectangular piece of cardboard of size 16 inches by 24 inches by cutting 4 squares of equal size from the corners and folding up the, whoops, see, that's a typo, sides, not size. Let x represent the length of the side of each square. Write a function for the volume of the resulting box. And we want this to be a function of x. And then we're going to find the domain of the function given the physical constraints, and what is the volume of the box if squares of size 4 by 4 inches are cut from each corner. Okay, so let's do part A first. It helps me to draw pictures. So we've got a rectangle. In theory, it's a rectangle. Mine is a mess. So you've got 16 inches, 24 inches here, right? And then we're going to cut 4 squares from the corner. They're all the same size. And then this is actually cut out, and this part's folded up. And so the base ends up not being 16 by 24 inches. It's going to be smaller, and it depends on how big these values of x are. These are all size x. So x is actually going to end up being the height. We know the volume of the box is the length times the width times the height. In this case, h ends up being x once you fold up those sides. So what is the length? The length is not going to be 24 inches, but 24 minus, notice you've taken out a length of x on both sides, so it's minus 2x. And then the width, so that's this in here, right? And the width is in here, is going to be not the 16 inches, but again, you're subtracting 2 lengths of x. So the volume, here volume is a function of length, width, and height. Now we're going to write it, just as a function of x. So the length is 24 minus 2x, the width is 16 minus 2x, and the height we said is x. There's our formula. Now you can expand that, but we're not going to do that. It's actually kind of useful to leave it in this form instead of getting all those higher powers. And then B, the domain, given the physical constraints. So we want to have a box here. So one thing is x, right? The domain is the set of all possible inputs, which is x. We don't want x to be 0, although technically it could be 0, but then you wouldn't have a box. So we're not going to let it be 0. We're going to say it has to be bigger than 0. The other thing that needs to happen then, we can't just say x can be as big as we want because we've got some restrictions here. This biggest x can be, you know, just use the picture here. It should make sense. If you're cutting squares, it can go up to 8 inches, but it can't get bigger than that. And on this side, it could go up to 12 inches, you know, 24 divided by 2 is 12, but it couldn't get bigger than that. Well, 8 is the smaller of those two numbers, so that's our domain. Whoops, I forgot my inequality sign. An interval notation that would look like that. We'll use this. Now you could use algebra to do this. I just used the picture and, you know, thinking about it. But, you know, every one of these dimensions has to be greater than 0, not just this one. So if you solve any of these, make them greater than 0, you're going to get the result that we got here. Here you'd have negative 2x is greater than 24. Divide by negative 2, x is less than, whoops, negative 24, x is less than 12. And that's what I was talking about for this dimension. And then you can do it again for the other. 16 minus 2x needs to be greater than 0. Negative 2x greater than negative 16. So x is greater than 8. Well, you have to take the smaller, or x is less than 8. Sorry, I said greater than, didn't I? You have to take the smaller of the two, because if this becomes bigger than 8, then you don't have the width. Okay, C. So you've got to consider those physical constraints of the lengths of your sides. What is the volume if squares of size 4 by 4 inches are cut from each corner? Well, that just means find V at 4. So you're just going to plug 4 into your formula. Again, you don't have to expand this to do that. You can just plug it in right where the x's are. It's actually easier than having to cube. If you expand this, you're going to have to cube 4, and then you've got bigger powers. Okay, 24 minus 8 is 16. 16 minus 8 is 8, and then times 4. Oh, let's see, that's 16 times 32. And I'm gonna use a calculator. Not too late. Well, by the time I find my calculator, I probably could just here it is. Just have done it myself because I'm pretty fast. Inches cubed. Okay. Don't forget the appropriate label. This is a volume, so it should be cubic inches. Next one. We have, let's see, we're going to inscribe a rectangle in this semicircle. So this is actually the semicircle. I included a graph. This is the y is 16 minus x squared. If you graph that, that's what you'll get. The base of the rectangle is on the x-axis, and two vertices are always on the semicircle. So what you have to keep in mind is this is not a constant here. You could get different rectangles, right? Here could be a different possibility, but you are restricted to having those two vertices on the semicircle and the base on the x-axis. So what is the area of the rectangle as a function of x? All right, and then what's the domain? Again, we can use the picture to help us with that. Just a second. Okay. So we know from geometry that area is length times width, right? So we want to write this area so that if we know the thing that we know here is, given any particular rectangle, we can find x and y. So if we know just the x coordinate, can we plug in that value and get the area of the resulting rectangle? That's what you're trying to do here. Well, if you think about this in terms of the plane, let's call the base the length and the height the width. Of course, you could flip that. Notice that the length of this rectangle is related to the x coordinate. The x coordinate, and we're just going to use the positive x coordinate because that makes sense, right? Here's x. The length is going to be twice x. So if we know what x is, we can find the length. The other thing we know is the y. The y coordinate, now it's not going to be given to us directly because we're only given x, but we can use this formula here to find what y is. Y is 16 minus x squared. So the height of this rectangle is actually, or the width, I guess we called it the width, right? Is y, which is 16 minus x squared. Let me write that all down. So the length is 2x, and then y is actually the width. Now this is a function of x and y. We want just a function of x, so we need to write y as its formula, 16 minus x squared. And now I'll use function notation. A at x is 2x times the square root of 16 minus x squared is our function. Now all we need is a given x coordinate, and we can find the area. But what are the restrictions here? It's easiest just use the picture to think about that. X, for one thing, to get a positive result, we need x to be positive, a positive result for our area. And then notice the biggest x can be is 4. So the domain, x needs to be between 0 and 4 units. Okay, we've got 2 more problems. I'm going to take another little break here because somebody's knocking at my door, I can tell, quietly.